Okay, so what is force? Well, by definition, force is just a pull or push that acts on an object. So this is just a pull or push that acts on an object. Now, with the definition out of the way, so you can just use this basic definition. So the definition out of the way, the next thing that you need to understand are the units of force. So the units of force are the newtons. So the unit of force is the newton. So this is the overall unit, the newton. But sometimes you look at the unit of force in terms of what it is actually made of. Later on, we'll see a formula like F is equals to ma, which will show you that the newton, which is the unit of force, is actually made out of a kg that comes from the mass here. And then from acceleration, you have the meter per second squared. So in other words, we can look at the newton to be made out of these units. So sometimes they'll ask you, I think I've seen a multiple choice question, I will share it in the group later on, where they ask to say, what is the name of a force? So follow how I'm describing this question. They'll ask you to say, what is the name of a force? So what is the name of a force that gives a mass of 1 kg, an acceleration of 1 meter per second squared. So this statement, if you look at it, they are asking what this will be if the mass is 1 kg and the acceleration is 1 meter per second squared. The name of that force is actually just a newton. So the answer to this is a newton. That's the name of the force that gives a mass of 1 kg, an acceleration of 1 meter per second squared. So I was just mentioning this because sometimes the unit for force can be expressed as a kg, meter. Instead of writing that per, I can write it as that second with the -2 on top. So this can also be looked at as a unit of force. So of course you can see it is a derived unit. So the other thing that we have to keep in mind is, so of course this was just a detour. The third thing that we want to keep in mind when it comes to force is its nature. So by nature, I mean whether it's a vector or a scalar quantity. So force, of course, you guys should know to say it's a vector quantity, meaning it has both magnitude and direction. To describe it, you give a value to say 10 newtons or 50 newtons, but you also have to specify the direction in which that force is acting. Is it to the right, to the left, and so on? Okay, so yeah, that is basically what. Any questions so far? Okay. So yeah, as you can see, I can follow through in the chat section. I have 2 devices connected. So if you guys have a question, you can talk to me. Just go right ahead and type your question. I will be able to respond to you from there. Okay, so this is what force is so far. Now, having described force in general, there are a few things that we also just want to know about forces. And for now, let's look at the issue of resultant force. So let's look at what the resultant force is. So when it comes to resultant force, I'll go through this very quickly. It's something that we'll be using literally everywhere else after this, but let's just understand what it is for now. The resultant force is just a total, or more like an effective force that is acting on an object. Picture an object that is like this here. So picture something like a box like this that rests on a horizontal surface like this. So what you have to see is that if it is under the influence of multiple forces, so we can say that we have a force that is acting in this direction, and then we have another force, let's say something like this, and then we have all these forces are acting on this object. We can say this is F1 and this is F2. So the resultant force can be written sometimes as a sum of the forces, just an addition of F1 and F2, but taking into account the directions in which these forces are going. This is going to the right, this is also going to the right. So in this case, you just have to add them. They are both positive forces. But if you had, let's say, one of these, maybe one of these was negative, let's say this one here, let's put it as maybe something like this. What you should see here is that F1 will be to the right, so it will be positive, but F2 will be to the left. So we'll put this with the minus here. A good example I would give is, let's say we have something, the same setup, but now let's put values there. Now, so far, when I'm doing these like this, they are very basic and so on. But when we'll be looking at this, you guys, with so many lines on the diagrams, it might come out a little bit tricky. That's why perhaps I'm even taking time to run you through questions, even though I feel you guys are looking at this and say, well, that's too basic and so on. Let's say you have 10 newtons there, and then you have 6 newtons here. So if you try to find the resultant force here, I can say resultant force, I can say the sum of the forces, or I can say net force. In this case, the 10 newtons is to the right, so I'll take it as positive. The 6 newtons is to the left, so I'll take it as negative. And then when we add, we get that 4 newtons. So this becomes the net force on this setup. So it's something that is literally everywhere. We can have maybe multiple forces, not just 2. We can even have up to 4, 5 or more forces acting on our system. And we can have this. We can have another one. We can even have another one like that. Let's say 4, 5, and let's say 9. So we can see that the net force here will just be equal to the 9 is to the right, so positive. The 4 is to the left, so I can say negative. The 5 is to the right, so positive here. And then when we add all these, this gives us 5 here. Then plus this 5, which was at the end, we get 10 newtons. So the resultant force will be to the right. So this is how we approach the concept of net force. Now, before we proceed, forces tend to cause different results on an object. For example, when you have, let's say you have a water bottle. Let's say you have a bottle of some form, a plastic water bottle. And then you decide to compress, or let's say apply a force with your left hand in this direction and apply another force with your right hand in this direction. What you end up with is something like this. The bottle will be more like deformed. So what I'm trying to say here is forces can tend to cause deformation. They can change the shape of the object. They can deform this. Forces will have several results when applied to objects. They can deform the object. They can cause the object to move. They can literally damage the object. But mainly, you talk about deformation of an object. They change the shape. And then we also talk about forces changing the motion of an object. In this unit, our focus will be on that second function, how forces can change the motion of an object. So the next part of our unit will be to discuss how forces influence the motion of an object. So the effects of forces on the motion of an object. So this is what we want to describe next. Now, the description of the effects of forces on the motion of an object, this is actually what leads us or forces us to look at Newton's laws of motion. So this is what leads us to look at Newton's laws of motion. Because Newton's laws of motion actually govern, or they tell us how forces affect the motion of an object. Newton came up with 3 laws altogether. The first one, also called the law of inertia. So it's nicknamed the law of inertia because they have a similar interpretation. The second one, on the other hand, it's abbreviated by its formula. F is equals to ma. This is the most widely used equation, I think, in physics, or for this level. This equation keeps coming over and over and over. Now, apart from that, the third law that Newton came up with, we can abbreviate it as the action and reaction law. So these are the three laws that Newton came up with. Now, for you guys, these laws will be everything that you need to understand in terms of motion. They are very powerful in predicting the position of an object, especially when it comes to big objects, like, let's say, a car. You can predict where a car will be after, let's say, a few hours of motion or a few minutes of motion. You can even predict how, let's say, if you know, to say you have a runner, like Usain Bolt, for example, and then he's running on a straight road with a given speed, you can predict how long it would take him to cover a distance of, let's say, 400 meters or 100 meters. You can make all those predictions using the laws that Newton came up with. So, however, they tend to lose it when it comes to very, very small particles like electrons and so on. So there we use something else. But for you guys, everything that you look at is all about very big objects like boxes or people or cars. So these laws will be sufficient, or they'll be enough to help you. Now let's look at these laws one at a time so that you guys know exactly what they are. So let's start with Newton's first law. In his first law, Newton talks about an object that is either at rest or an object that is moving. So he points out to say that if an object is at rest, so an object at rest or an object in motion, in uniform motion. If you have an object that is at rest, or you have an object that is in uniform motion, that object will continue in its state of uniform motion. So continues, it will continue in its state. So if it's in its state of rest, it will continue in its state of rest. If it's in a state of uniform motion, it will continue being in that state of uniform motion unless acted upon by an external force. So unless acted upon by an external force. What does this statement mean? An easy interpretation of this statement that I can give you guys is, imagine if you have money and then you leave money in a room. You have some notes of money and then you leave them in your room on a table perhaps. So you leave a bill on a table. What Newton predicted was, let's say the windows are closed, as in there's no air blowing in your room or something. There are no, let's say there are no animals. There's only you and your roommate, or maybe you've got 4 roommates in your room. There are only the 4 of you. There are no animals getting into your room like rats and so on. There's no wind blowing and so on. And then you leave a bill on your table. What Newton's law predicts is that when you leave it on your table, it's in a state of rest. That a bill is at rest. He predicted that this bill will remain in its state of rest. It will remain on that table throughout. If you come back to your room after a week, you should find it exactly where you left it. Now, the only way that this bill would move from here, even if it means just moving from here to a different place, the only way it would move from here, it's only if it gets acted upon by an external force. So if there's you and 3 other people in your room, it would mean that the external force could have only been supplied by one of your roommates. So that's typically that. So like, for example, the same example I was giving you to say that it is you and your roommates, you're in a room, and then you leave let's say $200. That's a lot. You just leave maybe some amount of money on a table, and then you go out. You're sure you left your money there. you expect that that money is supposed to be there. If it moves, your immediate reaction would be like, maybe one of your roommates got that money and maybe put it somewhere, or maybe they got it and just got it. So that's typically what Newton's law is all about. If something is at rest, it is supposed to remain in that same position at rest, unless if someone else or maybe some other object comes to force it to move. Now, the external force here is not limited to just people. I was just using this example just for practice sake. It's not limited to people. If your windows are open, the external force can be the wind blowing your money away. If you have other things interacting with your money, like let's say you have rats in your room or something, they can maybe just bash into that amount, that note, and then maybe it falls off or something. So that would create that external force Newton was talking about. But this is if it is at rest. What if it is in motion? To describe the second part for if it is in motion, I'd like you to think about some slippery place, like let's say an icy surface. If you are, let's say, on an icy surface and then you're moving, let's say you push a box on an icy surface, what you expect is that on an icy surface, the box will keep sliding. It will be sliding. It will keep going. It might slide very, very far. If it were very, very slippery, it might keep sliding for, let's say, a very long period of time. The only way it would stop is if you had some disturbance somewhere here, so that it comes to bash into that disturbance. So this would create the external force that would force your object to stop. In fact, if you have a very smooth road, and then your car is being driven on a very smooth road, and then you try to, let's say it was moving already, and then you try to apply the brakes, the wheels would just start spinning, but the car will keep on going. Why? The surface is very smooth. The car just rolls over. The only way it would stop is if it bumps into something, or if the ground starts exerting a force, making the car to stop. So in this law, in the same first law, Newton talks about an object. If it is moving, it will keep moving. It will keep on moving unless if it is acted upon by an external force. A good application of this concept is satellites in orbit. You guys know to say that we have our planet, and then these countries within our funds, they have their satellites which rotate around the Earth. So it's like you have the Earth somewhere here, and then we have satellites which are literally in orbit, and they just rotate around the Earth like that. So if we make something like this, what you should ask yourself, how do they make sure that the satellites just keep on going like that? Well, here it's very simple. Outside the Earth's atmosphere, we have a place where, let's say, there's zero gravity. I hope you guys have heard that. If not heard, at least you might have seen it in movies or something, where if you were there as a person, you'd just be floating. You don't fall down or something due to gravity. So that acceleration due to gravity is not there. So because this is in zero gravity, there's no force, in other words, that is actually influencing these satellites. So when they give them an initial push in some direction, the satellite starts to rotate, and that rotation is maintained throughout. If nothing gets to bump into that satellite, it is expected to keep on orbiting like that throughout for a very, very long time. The only way it would change its direction or change its motion or anything is if there is an external force to act on it. So this is literally what Newton's first law was all about. Some other examples that I can give you over the same is you in a car. I don't know if you guys ever observed this, but if you've looked at these laws, let's say in high school or something, you'd have talked about a case where you are in a car. So you have a car that is being driven, and then this is you or something, and then you have a seat, something like this. when the brakes are applied suddenly, you tend to, if the car was moving forward and then the brakes are applied, the car stops immediately. What would happen is that you tend to lean forward. Why? Your body wants to keep moving with the same velocity the car had. So it's like you want to stop. The car is stopping. You were moving with the same velocity as the car, but the car has stopped. Your body wants to keep on moving. So we're still seeing Newton's first law here. But the best way of looking at this example is through the concept of inertia. The law of inertia just says one thing, or the concept of inertia. If we were to define inertia, we just say it is a tendency of an object to resist change in motion. So inertia is a tendency of an object to resist change in its motion. What does this imply? Well, it just describes exactly what we are looking at here. If you were moving in some direction and then the car stops, your body wants to keep moving. It's like your body is resisting that stopping the car is actually doing. So it wants to continue moving with the same speed that the car was moving at. Now, this description, this statement of what inertia is, it is directly related to the definition or the statement that Newton made in his first law. In his first law, he says, if an object is at rest, it will remain at rest. If an object is moving, it will continue moving. Well, this is exactly what inertia is saying, because inertia is just saying that it's the tendency of an object to resist a change in motion. What does that mean? If an object is at rest, the tendency will be to continue being at rest. If an object is in motion, the idea will be to continue in that state of motion. So the only thing that makes it to stop doing that would be an external force again, the same thing that Newton's first law talks about. So this resemblance in the two is the reason why Newton's first law is also called the law of inertia. Now, if you pay attention to inertia a little bit more, what you notice is that the larger the object, as in the greater the mass of an object, the greater the inertia. So I said MA, just M. If an object has a very large mass, then we expect that even the inertia here will also be very large. So inertia is proportional to the mass of an object. This is the reason why if you have a massive object, like for example, a truck, it takes a lot to actually make a truck to start moving. If you have, let's say, a truck standing on, let's say, on a road, and then we have let's say, robots, and then you have a small car as well, also at the same place with the truck, and then the robots suddenly turn green, meaning that the car and the truck can now start going forward. What you will see is that after, let's say, 5 seconds, the car would have gone, maybe it is somewhere there. The truck is still just somewhere here. Why? The car is very small. Its resistance to change is very small as well. So because it has a small mass, they were both at rest. So inertia will want them to keep on being at rest, but the resistance to remain, to moving, let's say, that tendency to remain at rest, it will be smaller for a small mass, but it will be bigger for a big mass. This is the reason why the truck will resist moving more than a small car. So in the same time, given the same period of time, the car will accelerate very fast to a high speed and cover a very big distance. But the truck, on the other hand, will just be accelerating slower as compared to the small car. The same thing can be observed when they are approaching the robots. If they are moving at the same speed, let's say you have a truck moving at 80 kilometers per hour, And then you have a small car as well, moving at the same speed. If they are approaching robots, which are, let's say, somewhere here, the one driving the small car can even come close with the same speed, closer to the robot, and then apply the brakes. Why? Because even though it is moving at a high speed, it doesn't resist the change. It will easily stop in a very short period of time. But the truck will resist the change. So if you tried to stop here, what you'll notice is that the truck might actually bypass the robots and stop at a further point. So the one driving the truck would tend to apply the brakes while still very far. So maybe this guy applies the brakes somewhere here so that at least he gives the truck enough time to get to stop when it is closer to the robots. Why is it like this? Because its tendency to resist is greater. In this case, it is resisting to stop. In the first part, it was resisting to move. Here now, it is resisting to stop. Okay, so this is what inertia is, and yeah, this is how it applies to Newton's first law of motion. There's more that I can say when it comes to inertia and Newton's first law. For example, when it comes to a car, we have things like seat belts, which are put in place just to protect you from the effects of inertia in Newton's first law. I don't know if you guys have ever been in a car accident before. Of course, not a good thing, but I don't know if anyone has been there before. I once stood or maybe saw the aftermath of a car accident where you have a car which apparently maybe hit into something. A person who was inside the car will be found sometimes. They'll be found somewhere ahead. It's like the person was thrown to act like a projectile, and then they are tossed, and then they get to fall somewhere ahead. But the car crash took place maybe somewhere this side. But the person is found maybe 50 kilometers in front or something. Not 50 kilometers, a little bit too much. Maybe a kilometer in front. Now the question is, how does the person find himself a kilometer in front ahead of the car crash? How does this happen? Well, the same thing of inertia. The car crash takes place here. The car stops after the car crash, but the person maintains his velocity. Why? Due to inertia. And that velocity throws the person through the window of the car, and the person behaves as a projectile until when they land somewhere in front. So this is how these events actually happen. So it's common for if you have a pickup truck or those counter trucks or vehicles where people are, for some reason, you agree to sit behind. Let's say you get to sit somewhere here. And then the person driving is driving maybe this a little bit too fast. Don't mind my drawings, you guys. I'm not trying to be an artist. Just try to make sure you understand what I'm describing here. The person driving this is a little bit too reckless and they hit into something. Or maybe they're not reckless, just something unfortunate happens. They hit into something. You who is behind, because there's nothing really helping you, there are two scenarios. Either the car will toss you due to inertia. You'll be tossed to hit in the back of the van there. Or if not that, you can actually be thrown to go in this manner. If you go in this manner, the car crash takes place here, but you might land in front of the car. Okay. So you might land in front of the car.
And to move forward once the car stops.
No, it's not the external force that causes the person to move forward. It's like this. When the car is moving, you are in the car. So since you are in the car and the car is moving, the idea here is that the velocity of the car will be the same as your velocity. So picture a car like this that is moving forward, and it is moving with a velocity of, let's say, 100 kilometers per hour. since the car is moving forward, even you who is here, let's say you are here, even you who is here, you have the same velocity. Your velocity will be the same as the velocity of the car, 100 kilometers per hour. But if the car suddenly hits an obstacle, maybe it hits into a tree or something, or another car, what happens is that this, by the way, happens if you are not wearing a seatbelt. So now I'm giving you a reason to be wearing your seatbelt every time when you get in a car. Of course, if your seat allows you for that. So if you're not wearing a seatbelt, what would happen is this obstacle forces the car to stop. The car is forced because it can't really bypass or go through this thing. So once it hits through this, the frame of the car, the whole lot of the car stops. But you who is just seated in the car, you do not hit the frame. You do not hit this object. So implying that you will keep moving with the same velocity that you had, that 100 kilometers per hour. So it's your body resisting the change. The car is saying, my friend, let's stop here. We've hit into something. But your body says, nah, I still have that 100 kilometers. I will continue moving. So that is inertia. That is what inertia is all about. Because of that, you'll be thrown through the window. And you keep moving with that. That 100 kilometers will toss you out as if you're a projectile now. And then you will land a little bit in front. But what car manufacturers do, they configure a seat belt. So the seat belt will come like this and it will hold you to the seat so that if the car stops, you stop with the car. Now, notice that the seat belt is not meant to make you stop immediately when the car hits into an obstacle. But when the car hits into an obstacle, the seat belt will allow you to move forward just a little bit, but it doesn't allow you to go through the window. And it doesn't allow you to hit the dashboard. It just allows you to move in front for a little bit, giving your body some amount of time to stop. And then eventually you stop. So in this case, notice that the seatbelt gives your body an external force that prevents your body to go through the window like that. Do you see that? Okay. So this is just one example of inertia and how it actually works. So, and this brings us to the conclusion of Newton's first law and leaving us with Newton's second law to describe. So everything we are doing so far is all theory, just consuming information, understanding what these laws are. And then in our next class, we're now going to look at how to actually apply these laws for different setups. And the most complicated setup that we're going to spend a lot of time on is going to be the inclined plane. So look out for that. That will be tomorrow night. So let's look at Newton's second law. In his second law now, Newton came up with a relationship between force and the acceleration that an object is going to have. So he noticed that when the force, and again, the reason why I described forces at first before I even started this, because in his law, the force that he's describing, it's not just a force, it is the net force. So he came up with an expression that relates the net force acting on an object to how it relates to the acceleration that an object is going to have. Now, how it goes, he observed that the acceleration of an object will actually be proportional to the force that is an unbalanced force acting on the object, but it will be inversely proportional to the mass of that object, to the mass. Put it as an expression, it gives rise to the equation acceleration is equals to force over the mass, such that in the end, we get the famous equation F is equals to ma. Now, in physics, in most cases, if you don't remember the exact definition, you can just relate the equation as well. You just describe the equation, and that can be accepted as an answer too. So you can just say, Newton's second law states that the acceleration of an object is equals to the is equals to the force that is causing the object to accelerate divided by the mass of that object. That can also be accepted as Newton's second law. So it's equals to the force causing the object to accelerate divided by the mass of that object. So you can define Newton's second law based on this equation. So with that in mind, this equation is the expression that we'll be using over and over in this discussion. So just look out for that, you guys. Understand what it implies. Not to say that this expression that is here is actually a net force, not just one force. So that will come in handy later on. So there's really nothing much when it comes to the second law, except what this equation is and how to use it. So how to use it again, it will be what we'll be discussing tomorrow night and on Thursday night, how to use this same equation. But in most cases, we'll be using this equation hand in hand with the other concepts as well. Okay, but before we move on, let me just give a simple example for you guys to just picture what the second law is. Example 1 for the second law. Let's consider an object like this. And let's say this object has a mass of, we can give it 10 kgs. And it is on a smooth surface, something like this. And let's give it something like that. And let's argue that it experiences two forces. A force like this, let's say this force is, we can say 80 newtons. And a force like this, let's say 30 newtons. And the question is, what is the acceleration? So again, this is just something basic, you guys. But when we move on, of course, questions are going to start getting more and more weird. So what is the acceleration below? So let's see what is happening here. So in this case, of course, first you have F is equals to ma. So there are two forces, you have to combine them. So let's get what the net force is. So the 80 is to the right, so we'll have positive 80. And then we have the 30 is to the left, we have minus 30. And then this is what is equals to ma. So the m is the mass, we have 10 here, the acceleration. Then the difference here is just a 50. So we divide both sides by 10, this cancels. We get the acceleration as 10 into 50. So that becomes 5 meters per second squared. So this is a simple way we use this expression. Okay, so yeah, this is Newton's second law. And next up, Newton's third law. Okay, so simple as it might be, by the time we start looking at these expressions, you will see how complicated sometimes these ideas get. But for now, I'm starting with the basics, and then we'll start complicating them as we go. Now, Newton's third law, perhaps the easiest of the bunch. Newton's third law just talks about one thing. For every action, there will be an equal but opposite reaction. There is an equal but opposite reaction. Now, this statement has a lot of applications. It can be traced to many ideas in engineering and also to everyday activities. Now, the easiest way that you can actually picture it is if you have an object like this that is resting on a surface. So let's say you have something like this and it is resting on a surface. What you see here is that the weight of this object will be going vertically downwards. So the weight will be going vertically downwards. But what Newton's third law says is we will also have a reaction from here. The reaction will be the same as this, but it will be opposite in direction. So we are going to have a reaction that goes something like this. So let's say reaction. So this is what we're going to have here, according to Newton's third law. Now, to understand what the reaction here is going to be, we are going to define a concept that we call a normal force. So we're going to describe a normal force. I think it will be part of the last two things that we'll actually look at tonight. The normal force. Now, what is the normal force? Well, the normal force is a reaction force. The normal force is a reaction force. It's a force that is more like a reaction of a surface whenever a force is acting on it. So every time when you want to find where the normal force is, I want you to first look at where the surface is. If you have a surface like this one here, so let's sum this up. So if you have a surface like this one here, where we have something like this, what will happen here is that if you have a surface like this one, then we place an object on our surface here. So let's place our object here. What happens here is that the normal force, it's a force that will act from the surface onto the object, and it always acts perpendicular to the surface. Since the surface is a horizontal surface, the normal force will act from the surface, perpendicular to the surface, and it acts onto the object, implying that it will come from here, it will be acting onto the object, the normal force will act in this direction. So if you look at this part where we're describing the reaction force, notice that the reaction force that we actually observe here, it's actually the same normal force that we're just describing down here. So that here, when it comes to the reaction force from this surface, it's actually just the normal force. I can just use N for our normal force there. Now, let's continue with the normal force idea. If let's say you have a surface like, let's say a surface like this. So if this is your surface here, and then we have an object on the surface that is like this, and then we are looking for the normal force. So the normal force, remember by description, it acts, you have two things, from the surface. It acts from the surface to the object, and it always acts perpendicular to the surface. What this implies is that since now our surface is a slanting line like this, then we have to ask ourselves, what does perpendicular to this line, this surface, imply? Well, perpendicular will mean something like this. Anything acting along this line will be perpendicular to the surface. Now, the first statement was it acts from the surface onto the object. So from the surface onto the object will mean the normal force will have to be a line like this one. So this will be our normal force. So this is where the normal force is going to be. And the next thing, and perhaps the last surface that I'll show you guys, is picture something like this, a surface like this. Let's say you have a surface that is like this, a surface that is vertical. And then you have an object that is actually sliding on this surface. Now, all these cases that I'm describing here, they are cases that we will look at when we start looking at the complicated ideas later on. So I just want us to understand where the surface is for all these different cases. So consider an object like this that is sliding down on our surface being that vertical yellow line. So where will our normal point, where will it be? Well, again, we are saying it has to be perpendicular to the surface. Perpendicular to that yellow line has to be something that acts in this direction, horizontal. So either to the right or to the left. Then the first point, it has to be, our normal force must act from the surface onto the object. So since it has to be from the surface, then it means that our normal force must actually lie in this direction. So we see that in this case, the normal force will be something like that. Now, I want you guys to observe one thing here. A common mistake that students will get is the thinking that the normal force will always be perpendicular, as in it will always point upwards. Students will want to think that the normal force will always point upwards, which is not true, because you've seen the direction of the normal depends on, one, how the surface is. If the surface is horizontal, the normal will be perpendicular and it will point up. If the surface is slanting like this, we sort to say, then the normal will have to be something that points in a weird way. This is going to be what we'll see when we start looking at inclined planes. And if the surface is vertical, then we see the normal gets to be horizontal. So all these are different scenarios that we will look at in more examples tomorrow. To conclude, we end this class by looking at friction. What is friction? Friction is a force that always opposes motion. So this is a force that opposes motion. So it's a force that opposes motion. So whenever you want to find where friction is pointing, ask yourself, where is the motion pointing? So if you have an object like this, and this object is on a surface like this, and the object is going forward, the motion is forward, then friction will be back. If you have an object that is, let's say, on an inclined plane, and the object is sliding on an inclined plane, let's say it's sliding down. If this is what you have, then friction will point backwards. So every time when describing friction, just ask yourself, the question will always give you a hint where friction is, where the motion is. Picture this case where the wall was vertical, and then you have an object that was sliding down along our wall. So if this is what you have, again, the question is, where is friction? So if this object is sliding downwards, so this is the motion, then notice that friction has to oppose this. Friction has to point upwards. So friction will always oppose your motion. If motion is down, friction is up. If motion is up, friction is down. If motion is to the right, friction is to the left. So this is literally how friction behaves relative to what motion is. But there is a special thing or an equation that gives us or predicts what the friction will be. So this actually is called the coefficient of friction. So this is the coefficient of friction. The coefficient of friction, mu, it's a ratio that relates the force of friction to the normal force that is present. So mostly I'll use Fn to mean the force of friction, the normal force. And I'll use Ff to mean the force of friction. So I'm using this to mean the force of friction or frictional force. And then I'll use Fn to mean the force normal or the normal force. So this ratio, when you look at it, the friction comes with a unit of Newton, because remember, friction is a force. So it comes with units of Newton. The force normal as well, it's a force. This is also a force. So it also has the unit of Newton. So when you divide these two, you notice that the answer you get will not have a unit. In other words, this coefficient of friction, it has no units. One other thing that I would want you to keep in mind when it comes to this coefficient of friction is that it will always be a number from 0 to 1. Actually, in most calculations, this quantity mu, it will always be less than. It will always be, let me say, from 0, less than the coefficient, which is less than 1. This coefficient of friction, it will always be within this range. It can be 1, yes, but it's rare that it will be 1 in your calculations. But it can never be greater than 1. That has to be in your mind. You have to remember that. If in your calculations you find your coefficient is greater than 1, then be worried. It might mean that you made a mistake somewhere. So once you find that, just go through your calculations one more time to just ensure that you did not make a mistake. If when you check your calculations and you find that you did not make a mistake somewhere and your answer is still over 1, then maybe you might leave it just like that. But overall, this coefficient is a number that is less than 1. Unless if a question just had an error in its phrasing, or when the time we are giving you our question, the values there, then you might end up with a value greater than, but almost always, I've only seen one case where the number was greater than 1, and that question had a mistake. But everywhere else, this number is always 0.2, 0.0 something, or maybe 0.4, 0.8, but always less than 1. So this is what the coefficient of friction is. So if you look at it, it's like we have the coefficient is equals to force of friction over the normal force, implying that we can say the force of friction is equals to the coefficient of friction multiplying the force normal. Now, what does this coefficient of friction actually give us? It's a description of how rough a surface is. If you have a tarmac that is very, very rough, you expect that the coefficient there is going to be very, very, very big, closer to 1. If you have a surface that is very, very smooth, if it is very, very smooth, then it means that the coefficient there is going to be very, very small. So it tells us how much friction a surface is going to have. If the coefficient is very big, the surface is going to be very rough, and friction experienced there is going to be a lot. If a surface is very smooth, like an icy surface, you expect the coefficient to be very, very small, closer to 0, not 0, closer to 0. And if the coefficient is closer to 0, then friction will be very, very small there. So this is what the coefficient of friction is all about. Okay, so we're going to end here. Tomorrow when we meet, I've run through this to describe everything that you need to know under forces. The next 2 classes we're going to have will be example, showing you guys how we use the knowledge that we've made tonight, or that we've gone through tonight, to work out any question that we'll find under forces. So do we have any questions before we say goodnight?
So the physics test 1, tell me what's the choice?
Okay, so let me stop recording.